Recently, we talked about importance of plots, importance of visualization, and actually you can also visualize the quantiles. You can do it in several different ways. Let me show you some of them at least. Okay. The first plot you can use, I will call it percentile plot, where you visualize these two ways to represent your data, right? You kind of represent your data using two different entities. On one hand, you have the values. It's the real values that you measure. On the other hand, you have the sample quantiles. It's these percentages that you calculated, right? So the idea is simple. Let's use x-axis for the values. Let's use y-axis for the percentages. So we'll make a plot in Cartesian with Cartesian coordinates that corresponds to these two different representations. And this is what I call a percentiles plot. So you can see here you have the real values, here you have the percentages, and then you simply have the points which correspond to your sample. And you can see that I connect the points with a line. I don't know the real values which are between, for example, these 2 points. So the simplest way is just to use linear approximation. So I connect them with a line. Of course, the bigger sample size is, the more precise this plot will be. But even for a small sample size, this plot provides you some interesting information. For example, this is the position of the value number 5. It's 45th percentile, as you see, right? This is the position of the value number 6. It's 55th percentile. So apparently, the median will be located exactly in the middle. So you can kind of make a line, the horizontal line, which corresponds to the 50th percentile, and then where this line crosses the x-axis, that will be your median value, right? So that's one way to represent your sample. Using the percentiles. The second way is based on quartiles. So if you take the quartiles, I'll just remind you, the quartiles, it's the quantiles that split your data into 25, 25, 25% portions, right? The amount of values. And you can also use these statistics, these three statistics, together with mean and max, to make another plot, which is called a box and whiskers plot. So the idea is following. The quartiles, we will denote them as Q1, Q2, Q3. So Q1 gives you the boundary between 25% of smallest values and 75% of largest. Q2 is median, so it splits you 50-50, your values to 50-50 intervals. And then Q3 is the third quartile, so it gives you a boundary between 75% of smallest values and 25% of largest. Now you can add min and max, and then you can visualize this using this box and whiskers plot. So you can see box and whiskers. The box corresponds to the quartiles. So the left boundary is Q1, the right boundary is Q2, and then you can see the thick line in the middle, it's the median. And then the whiskers, like cats have, they show the position of the minimum and the maximum value. When you use a software to make box and whiskers plot, then you will sometimes find that actually the min and max, the whiskers do not correspond to min and max. For example, in this case, you can see that for the right plot, for the left plot, it looks good, but for the right plot, so the whisker is located here, while this point is kind of hanging, right? Why it happens? Because box and whiskers plot in most of the software, it has a built-in tool to detect outliers, and if it detects outliers, it shows outliers like separately. So let me explain this. So first of all, you can see that this is the plot in the same scale. And you can see this is the mean, the max, and the quartiles. And here you have mean and max and the quartiles, right? So apparently the whisker on the right plot does not correspond to mean. Now, this is how it works. This is how the detector works. So first of all, you compute the first and the third quartile. The distance between first and the third quartile is called interquartile range, IQR. If you have some outliers on both sides, up to 20%, up to 25%, then it will not change the position of Q1 and Q3. So they are very stable to outliers. Now, we can use this IQR as an outlier detector. How? Well, first of all, we stretch it. We multiply it to 1.5. And then we use this as a boundary. So we add this interval to Q1 on the left side of Q1. So mathematically, it's subtraction, right? So you take Q1 minus 1.5 IQR. And then we try to find, do we have any points in this area beyond Q1 minus 1.5 IQR? Well, apparently we don't have any. So we don't have any outliers on the left tail. Now we do the same for the right tail, right? So we take Q3 and add 1.5 IQR. And then again, we look for outliers here. So do we have any values that are beyond this limit? And indeed, we have one. So that's what is detected as outlier. So it means that it should be excluded and shown separately as outlier on the plot. And then we take the next value for the whisker. So that's why in this case, the box and whiskers plot looks a little bit different. So the detected outlier is shown separately, and then the whisker simply ends where the next largest value is. Okay. So why you have an outlier? Well, there are many reasons for that. First of all, and most of the time it's like this, it's a measurement error. So you did some wrong measurements. It can be also wrong object among other. For example, you have, you measure concentration of different chemicals in water from lake, and then suddenly you also have a tap water. Apparently, chemically, the tap water will be different from the water from the lake, right? But it also can be natural variability. Imagine, for example, height of people, and then usually people have height around maybe 160, 170 centimeters. And if you have a small sample size, like 10 people, and then suddenly one of them is, NBA player with 220, this person will be outlier. But there is nothing wrong to be 220. It's just a rare event, right? So it also be part of natural variability. So the idea is that if you have an outlier, you need to check and make sure that it's not the first two. So it's not a measurement error and it's not wrong object among other. If it's so, then you have to repeat this measurement. And you cannot use this value as a part of your statistical analysis. But if it's a natural variability, if you don't have any evidence against this outlier, then you cannot remove it. You need to either reconsider your sampling. Maybe your sample is not correct, your sampling is not good enough, or you just continue as it is. So you may have some extreme values in your sample, especially if sample size is small. There is nothing wrong with it. Okay. And then you can see that the box plot reflects distribution of your values very well, right? So if your distribution has a central tendency, so most of the values located in the center, you can clearly see it as a symmetric box plot, right? If your distribution is skewed, so it means that most of the values tend to be on the left side or on the right side of your x-axis, then you will also see it as presence of outliers or maybe longer whisker in the box plot. So box plot is very good for assessing how symmetric your distribution is. Also, box plot is good for comparing groups, just a visual comparison without any particular conclusions, just as a first step, so to speak. For example, in this case, you can see that I compare beer consumption, how much of beer people drink, for two groups of people. The first group is Scandinavians, that we will also use in the final example in this learning sequence, and then this is Mediterranean. And then you can see that the consumption of beer varies quite a lot. It's a number of liters per year, but you can see that like Scandinavians tend to drink more beer in this than the Mediterraneans, right? So in box plot clearly reflects it. Also, you have some overlapping. The boxes are clearly separated here, right? And then you can also represent it vertically, so it gives you the same picture. So box plots are pretty good for quick and dirty, like a first step analysis of your data. Just make sure that you have enough values, because you remember, to make a box plot, you need at least 5 statistics for every plot. So make sure that you have at least, 7, 8, 10 values when you make a box plot. Otherwise, it can look weird. Okay. And then the next couple of videos will be about a particular tool, which is a supplementary to this course. It's a tool, it's called Grasta. Grasta is a website which collects several interactive tools for learning statistics and a little bit other methods as well, which I created also specifically for this course. You can see that it has like different sections, like in this case, you can see section descriptive statistics and plots. And then if you click try on any app, you will be able to try this app and perhaps understand a little bit better a particular subject. For example, in the next couple of videos, I'll show you how to understand better this box plot, calculation and quantiles and quartiles, and also a little bit about this percentile plot. So it's first 2 apps. So simply watch these two videos first, and then go to grasta.com, and click try on each of these 2 apps and play with them. So hopefully it will give you a little bit better understanding of the concept behind these 2 plots. Okay. So watch these videos, play with the apps, and then come back.